earthquake threat in Oregon and explain what is being done to reduce future risks. Our speaker today is Professor of Geology and past chair of the Department of Geology at Portland State University, where he's taught for nearly 20 years. He specializes in environmental and engineering geology and has undertaken projects that involve mapping earthquakes, landslides, and other hazards. In 2001, he received the Distinguished Faculty Award from the Portland State Alumni Association. He has authored over 90 publications and has received more than 25 research grants. Our speaker's second book, Cataclysms on the Columbia, The Great Missoula Floods, was published in October of 2009. He received his bachelor's and master's degrees from Stanford University and his PhD in geology from the University of Colorado Boulder. Please help me welcome today's speaker, Scott Burns.
Well, this is a real pleasure to be able to come and talk to you about something that I am very, very excited about, and that's geology. And at Portland State University, my research program that I run there deals with all of the natural hazards, the geological hazards that we have got, and we've got lots of them here in the Portland area. And so we're going to focus in today on earthquakes. And welcome from Portland State. It's our largest university in the state. It's been that way for over 10 years. I've taught in Switzerland, New Zealand, Washington, and Colorado, and Louisiana before coming back to Portland. I grew up here. I'm a sixth-generation Oregonian. I love it being here, and I love teaching at Portland State, which is a dynamic and great place to teach and learn. And so thank you very much for the chance to come and talk. And I was a member of the City Club 12 to 14 years ago. And so it's fun to be back here. At that time, we were meeting in the Hilton Hotel. And especially with this month, with Turkey and Haiti and Chile having the large earthquakes we have, earthquakes are back on the radar screen, so let's talk a little bit about that. You probably don't realize it, but right now, all of us are moving. And in fact, the Earth that we are on, any place in the world, is always moving because we have a dynamic Earth. We have what we call plate tectonics. And what is happening every day at places called the ridges in the ocean, we are creating new Earth, new plates, and they are moving away from that, and then plates are running into one another, being subducted down underneath each other and being destroyed. And so we are on the North American plate. Our plate is being created out in the middle part of the Atlantic on what we call the Mid-Atlantic Ridge. It is moving in a westerly direction. We are moving about 4 centimeters a year, about as fast as your fingernail grows. And then we are hitting another small little plate that is off of the Pacific coast called the Juan de Fuca plate that is being generated at a chain of underwater volcanoes 200 miles off of the coast. And it is moving towards us at about the same rate, 4 centimeters a year. And what is happening is that Juan de Fuca plate is being subducted down underneath North America. And as it goes down, eventually it's going to melt, come back to the surface as a chain of volcanoes that we call the beautiful Cascade Mountains. We live on a subduction zone boundary. And we call it, in geology, the Cascadia margin. And it is dynamic, and because of that, we've got beautiful mountains. We got beautiful volcanoes, but at the same time, we also have earthquakes. And that is one of the facts of life living here in the Pacific Northwest. We have all of these different natural hazards. I deal with landslides, and we have a better way of being able to predict them. Volcanoes and volcanic hazards, and one of the best teams in the world is right across the river at Cascade Volcano Observatory. We can predict those. And rivers and flooding, we are doing a very, very good job of those. But earthquakes, that is a geological hazard that we still are quite a ways from being able to predict. So how about earthquakes in general, and why are we concerned about it? Well, it's our most dangerous of all of our geological hazards because it comes unannounced. And many of you probably have been in earthquakes, and all of a sudden it just starts shaking. So, oh my God, what's happening? Every year we have 800,000 earthquakes every year that are recorded on seismographs. About 100,000 of those are going to be felt by a lot of people. I love it when the Oregonian says, Klatsk and I had a 1.8 yesterday. Well, shoot, nobody even felt it, so why even put it in the newspaper? And then out of those 100,000 that are felt, about 1,000 of them cause damage, and of those 1,000 that cause damage, you have 10 on the average, really disastrous ones, and we've had 3 of those 10 in 1 month this year. And they also cause a lot of deaths, which became very apparent when we had Haiti. In the last 4,000 years, 13 million people have been killed worldwide from that. And in the last 100 years, 1 million people have been killed from that. On the average, it's 10,000 people a year are killed. Well, we've gone way beyond that just this particular month. Also, we talk about magnitudes, and what does magnitude mean? In the old days, we would call this the Richter scale magnitude. Now we've gone to a new scheme, which is kind of similar, called moment magnitude. And it's a scale that goes between 1 and 12. It's a logarithmic scale, but it also has a little fudge factor that is thrown in. Many of you probably remember back in 1993, we had the spring break quake. I still remember at 5:30 or thereabouts in the morning, get woken up by this. I was so excited about it. My wife said, "Why are you so excited about this?" Well, we don't get too many earthquakes around here. My kids were wondering, what do we do? That was a 5.6, and so use that as a baseline. If we go up to 6.6, which is one number above that, the amount of energy liberated by 6.6 is about 30 times. Then if we go up to 7.6, it's not 30 and another 30, it's 30 times 30, or 900 times the amount of energy that is liberated. And if we go up to 8.6, which is the next level, we're talking subduction zone type of earthquakes, and that's 30 times 30 times 30, 27,000 times the amount of shaking and the amount of energy that is liberated in that. And that's what we are really concerned about here in Oregon, the big one, which I'll talk about in a second. So what are the hazards that we have from earthquakes? And how can they affect loss of property, loss of life? There are four major ones that we deal with in the geological community. Number one is just ground shaking. And if a structure is built on ground as the energy is going through in these waves, it is going to possibly fall down, fall apart, or whatever it is. But then and so the closer you are to the epicenter, or the focus is in the ground, epicenter's on the surface, the closer you are, the more danger that you have got. Secondly, the bigger the magnitude, the more danger that you're going to be having, and the more destruction that you're going to be having. But in Portland, we add one additional thing, and that's what we call ground amplification. What you build on is very important. God had to have been a geologist. In the Bible, it says, build your house on the rock, not on the sand. And that's good geology. Because if an earthquake wave goes through solid bedrock, the structure will bend, but it'll go back to its original shape and form. Whereas if it's on sediment, unconsolidated sediment, it may shake, but it may not go back to the original form. And secondly, if you live on a big bowl of sediments, what will happen is the waves will get bigger. As the waves are coming in, all of a sudden, they go big. How do they do that? Well, think back to your days in middle school or in high school physics where you made wave tanks. Tank of water, generate waves that are going like this. What happens? They get to the other side, and that's just like earthquake wave. They'll bounce back, and so you're still generating waves, and when the waves come hit one another, they either cancel each other out or they add to each other, and that's what we call wave amplification. When we have earthquake waves, we have an earthquake at the beach. Earthquake waves come through the Coast Range, through the West Hills, into this big bowl of sediments that we call the Portland Basin. What will happen is those waves will come through, they'll hit the other side. Some of them are going to continue on through the Cascades, but other ones are going to bounce back. And so we are going to have wave amplification and nullification out there in the center of that bowl. We have the Tualatin Valley, 900 feet of sediments. Here, 1,500 feet of sediments as we go down the valley, down to Corvallis, down to Salem and Eugene. We also have a huge bowl of sediments that are there. And so we are very concerned about that amplification. Second hazard that we have is liquefaction. That's where the good solid ground turns into a liquid, flows, and a structure that may be right on it just sinks right into the ground. Or if you're on the side of a hill, what will happen, it'll just ooze out in what we call a lateral spread. What are the areas that are most prone to liquefaction? Two things, primarily sandy parent material and then high groundwater. Table that you've got. Where do you find that in Portland? Well, it's along the rivers. So the whole area along where the airport is, along the Columbia River on this side and the Washington side, Swan Island, some of the areas in downtown Portland, those are all liquefiable types of soils that we have got. Third hazard that we have are landslides. Steep slopes, if you also have a lot of water in them, and in the wintertime we've got a lot of moisture that is in them from the rainfall, you have 2 strikes against you. When you got that, all you need is that trigger of a very large earthquake, and you will have a landslide, and everything will come tumbling down. It's interesting, maybe some of you remember back in 2003, we had the 2nd largest earthquake recorded in the Pacific Northwest since the seismograph was invented. And we called it the Nisqually Earthquake. The epicenter was just north of Olympia. And it was 6.8. Now, it was deep. And it's actually in the Juan de Fuca plate that was down underneath the North American plate, but 6.8, second biggest. And I was supposed to be having some geologists with the highway department up there come down and talk to my students like 3 days later. I said, there's no way they're going to be here. They're going to be out working on landslides for the next 2 weeks, because it was in February that we had that. And so I said, oh my God, we're going to have lots and lots of earthquakes from this very, very large, or lots of landslides from the earthquakes. And then I called them up the next day, and they said, well, we're almost done mapping the landslides. And I said, what do you mean? They said, there are only 10 major ones. I said, this was a 6.8. It should be huge. He said, think of what's happened this last month. We had a drought. That whole February did not rain in the Pacific Northwest. The soils were well drained. And so the moisture plus the shaking was very important. So if we have a major earthquake in the middle part of the wintertime, we'll have lots of landslides. If we don't have it in the summertime, the end of the summertime, maybe not quite as many. And the last major hazard that we don't have in Portland, those are the 3 in Portland. The other one is along the coast, and those are tsunamis. Tsunamis are something that wasn't even on the radar screen up until 2004, when we had the great Indonesian earthquake that we had there. And then everybody started calling them tsunamis. I still remember making some comments on Bob Miller's KPAM 860 program in the morning. He kept on calling them tidal waves. And I said, no, Bob, they are tsunamis. It has nothing to do with the tidal waves, which is a Japanese term meaning seismic sea wave. What happens is when you have great shaking at the edge of the continental shelf, you'll have a lot of earthquakes, or landslides that will be occurring on the continental shelf. As those go down, they displace water and then create the waves. Also, just the change in the bottom of the ocean can create the waves. And so you will have this seismic sea wave that will come in onto the shore. One of the safest places to be during a tsunami is out in the middle of the ocean. These travel at 650 miles an hour. That's how we can calculate, if you have a big earthquake in Chile, when it's going to be hitting Japan and when it's going to be hitting Hilo, Hawaii. And so what will happen on your boat is just going to go up like this and go right back down. Maybe some of you remember the Ernest Borgnine movie, Poseidon Adventure, a few years ago. Ship out in the middle of the Mediterranean gets hit by a tsunami and flips over, and they have to make it to the top. Well, that geologically isn't correct. You're going to have, everything is going to be just going up and back down. But when those waves come close to shore, what's going to happen is they're going to start eroding the bottom, slowing down, what we call dragging bottom. They're going to rise up out of the water, and then that water is going to go inland. And we finally have very good photos and videos of this that we have gotten from Thailand and Indonesia, that people took pictures of this. And so now this is on the radar screen that we have got here. If we have a large subduction zone earthquake on the Oregon coast, I tell people when I give talks at the Oregon coast, if you are knocked to the ground and that earthquake lasts 2 to 3 minutes, don't wait for the authorities to tell you it's a subduction zone earthquake. Get the high ground. You got 20 to 30 minutes to get the high ground because of the potential for a tsunami. The people down in Concepcion in Chile last week were saying, oh, people didn't get in touch with us. Well, no, they aren't going to have any electricity. You're not going to have any electricity. And you need to get the higher ground at that particular time because of the chances of this happening. On our Oregon coast, most of our tsunamis will get to be about a maximum of 20 feet. The one that hit in Chile this last week was 7 feet high. We did find, one of our classes at Portland State did find some deposits in the back of Seaside 40 feet high, and that's awful. And so therefore, it means that we have had at least one that got that high in the past. But tsunamis are very important. Cannon Beach got on the bandwagon early. They said this is very important. We need to let everybody know if we have a tsunami either from a distance or locally. And they put in the loudspeaker system throughout the town. If you're down there at noon, all of a sudden at noon there will be, you'll have cows come on. Moo, moo. This is the tsunami warning system of Cannon Beach. In case of a potential tsunami, you will be alerted as to what to do, i.e. get to higher ground. And we now have all of those signs up and down the coast of you are entering the tsunami hazard zone, or you are exiting the tsunami hazard zone, or these are the evacuation routes. So we're much more prepared in that area. So how about earthquakes in the past in Oregon? Well, the seismograph was invented about 1880 or 1870. And actually, right afterwards, 1873, we had one of our largest earthquakes. Port Orford had a 6.3. The largest one in the Pacific Northwest was 1949. And it was a 7.1, again, very similar to the Nisqually one. It was just outside, the epicenter just outside of Olympia, Washington. And my old high school, Beaverton High School here, he had 3 floors. The whole third floor was completely condemned because of the shaking and breaking that occurred from that. And actually in Portland, we had quite a few deaths that occurred from that, and that was only a 7.1. And then in 1993, we had a 6.1 and a 6.0 down in Klamath Falls. I mentioned the 5.6 that occurred on spring break, also in 1993. But the one that I remember the most was 1962. It was in Portland. It was a 5.1. I was at a little Boy Scout meeting out in Beaverton, Oregon, in a grade school gym, concrete floor. We all got knocked to the ground. You could see the waves going across that concrete floor, and we said, what's going on? The ceiling looked like it was going to collapse, and it sticks in my mind to this day. And also that spring break quake of 1993, the Pioneer on the top of the Capitol building down in Salem got knocked 1 foot off of its pedestal, and the legislators said, oops, we might live in earthquake country. We better start investing in earthquake hazard maps, and we did at that particular time. And in fact, we have some of the best earthquake hazard maps that have been developed in the world. And we use the Oregon examples for that, the Portland area, the whole Willamette Valley, and then our tsunami maps. We have an absolutely wonderful geological survey here we call DOGAMI. And it's taxpayer money that is going into all of that, and it's money well spent. And that's from a person who is not associated with them. In Oregon, we have a lot of faults. That's where all of your earthquakes are going to be happening, where you're going to get movement on this. Well, the question is, in Oregon, we barely have all the maps, the faults mapped. But do we know, are they active or not? We don't have the foggiest idea. We have a long way to go. We look to our neighbors to the south, California. They have the Alquist-Priolo system down there, where they have a map of all of the major faults that have been found there. And then if you're going to be building, doing some construction or something in a particular area, you look it up, and they will tell you where the fault is it active or not? If it is active, when was the last time it went off? What's the maximum credible earthquake? And what's the recurrence interval? What are the chances of an earthquake occurring in that particular area? It'd be nice if we had that here in Oregon, because that would really help us in our planning. In Oregon, we have 3 sources for our major earthquakes. Remember, we have the North American plate going in this direction. The largest earthquakes that we can expect here are about 6.5 magnitude-wise. And how do we measure that? The longer the fault, the greater the potential magnitude that you've got. The Juan de Fuca plate that is being subducted underneath us has some larger ones, and they get up to about 7.3, 7.4. But it's where the 2 plates are coming together. They lock up as the Juan de Fuca plate is coming underneath us, and it builds up, and that lock zone goes all the way from Arcata, California, all the way up to Vancouver, British Columbia. Not only is it just in one place, but it may be 40, 50 miles wide. We don't know exactly. And when it breaks, it can potentially break the whole way. Sometimes it only breaks half of the way. So that is what we're most concerned with. Those are what we call subduction zone earthquakes. Those are going to be over 9 on the magnitude scale, last 2 to 3 minutes, and a lot of times have a tsunami generated 20 to 30 minutes after that earthquake occurs. Subduction zone earthquakes. When was the last one? It was 310 years ago, exactly. And it was on January 26th of the year 1700. And how do we know? At 9:30 in the night, how do we know that? Well, we went to Japan. Brian Atwater is the guy that finally realized that we had the potential for these large subduction zone earthquakes. He started publishing papers in 1984-85. He works with the U.S. Geological Survey out of Seattle. He said, we should be having these big ones. Then he started looking for examples along the coast, and he found these forests in Willapa Bay that were all dead. And he said, why? Well, the whole ground sunk. And they were in fresh water, and then they were in salt water as a result of that. And when we have a subduction zone earthquake, that's what happens. The whole coast sinks 1 to 2 meters down. And so he started looking at the records in Japan, and the Japanese are very, very good record keepers, and they had a tsunami. They hit from one end of the country to the other end of the country right then. It would have been January 27th, because they're another day later. It's 2 meters high, 6 feet high. And there was not one big earthquake there at that time, and no volcanic eruptions. So they said it's an orphan tsunami. It's from a faraway place. We have been dating buried soils up and down the coast. Brian in Washington, Kurt Peterson from my department here in Oregon, Gary Carver in Northern California, and they all come out about 300 years ago. So we were looking for an event 300 years ago, and we found it, and so that's why we use that date that it occurred. When was the previous one to that? About 800 years ago. Then when was the one before that? About 1,100 years. Because what we do is we drill down into the bay areas, into the marshlands that we have. Every time that there is an earthquake, the earth sinks, and that surface soil, the A horizon, the organic layer that is there, is now buried. And then every flood that occurs on the river will just keep burying it, burying and burying. And a lot of times, right after the whole coast sinks, then the tsunami comes in over the spit. All of that sand that is there is going to be deposited on the bottom of the bay, and many times we'll find a nice little sand layer on top of that buried A horizon. And so Kurt Peterson in our state, Mark D'Arienzo, they dated all of those particular soils going down there, and then they got, for the last 10,000 years, a whole bunch of different dates, and the recurrence interval is about every 500 years is when these occur. And so we'll talk a little bit about those in a second. Chris Goldfinger, who is a great professor down at Oregon State University in the School of Oceanography, he's been studying deposits off of the coast. Every time you have a big subduction zone earthquake, you shake it up, and you have these landslides that go off of the continental shelf down onto the abyssal plain that we have got out there on the Juan de Fuca plate. And then what he's doing is he's drilling out there and finding all these landslides and dating them. And he's got an absolutely wonderful record all the way from up in Vancouver all the way down to California. And what he has found is in the last 10,000 years, he has got 34 events that have occurred up and down the margin here of these turbidites, these major turbidites that he finds in all the different holes. 19 of them were found all the way from one end to the other. And then off the coast of northern Oregon, he has got about 24 recorded. Middle Oregon down near Newport, about 29, and then southern Oregon, about 34. So southern Oregon is much more active. As you go north, it gets less active. And so what we tell people is if you live on the Washington coast for having one of these big subduction zone earthquakes, it's about every 600 years that is going to be occurring. Northern Oregon, we say just about 480, 500 years. But southern Oregon, which is much more active, Chris says 287 miles, but basically 300 years. Every 300 years is the recurrence interval. So, when was the last major one that we had? It was 310 years ago, and that was from one end to the other end. You say, well, average, we still got 190 years to go. Remember, that's an average, and the range is anywhere from 200 years in between those events up to about 800 years. And so the potential of this happening is out there. In Portland, we have 3 major faults. We got one right in back of Portland. It's the Portland Hills Fault. When you fly into Portland, you look down, the edge of that mountain is straight line. Mother Nature is shouting out to us all of the time. When you see a straight line, it is telling you fault, fault, fault. Now, you got to prove that. And then we've got it there. Ian Maiden, a good friend of mine at Dogami, our state geological survey, has been studying this for the last 20 years, trying to find a place where it's offset so we can get something datable. Hasn't been real successful. So we really don't know, is it active or is it not? It has to be because we created the West Hills. But then secondly, what is the recurrence interval? When was the last time it went off? We don't really know. We also have one on the other side, the East Bank Fault. It runs parallel to this one. And then as you go up to Sylvan and cross down into Cedar Hills, you cross a third one that we call the Oakfield Fault. Those are the three major ones that we have. Some of these could possibly go up, if they're long enough that they could create up to a 6.5. But again, just like most of Oregon, we know where the faults are, but are they active? We just really don't know. We do have a Portland hazard map, and it is based on the soil and how is the soil going to respond to a movement on the Portland Hills Fault, subduction zone 1. And it's interesting. It goes from red to orange to gold to yellow. Yellow being the lowest earthquake activity, hazard, red being the highest. And we take into consideration the three hazards, the liquefaction, the landslides, and the ground amplification that we have got. So it's interesting. There are places like, if you go up to the zoo or the Children's Museum or Washington Park, those are our two most famous landslides. They are red because they're on an old landslide, and reactivation of an old landslide is very possible. You go out to the whole area along the Columbia River where the airport is, and then also the islands that are in the middle of the river, red. Swan Island, red, because it has liquefaction potential and then also ground amplification. The area in the Portland Quadrangle that has the least is Alameda Ridge, North Portland, which goes from Rocky Butte all the way out to St. John's. And it was created by the Great Missoula floods, which occurred 15 to 18,000 years ago as the floods came into Portland. It's like having a Rocky Butte, a big rock there, and it creates a pendant bar of sediment in background. And so we got about 200 feet of elevation that is out there. But if one geological hazard doesn't get you, another is the area of the highest radon in Portland. And probably in our work at Portland State has found that up to 90% of the houses have high radon problems that you've got there. Seismic building codes. When I moved back here to Portland, I got a hat from a friend of mine. And we were in Seismic Building Code 1. We were going to be shifting up to Seismic Building Code 2B because if you looked at the earthquake hazard map of the United States up until that time, you had three categories, red, orange, and green. Oregon was green. This was non-earthquake country. Earthquakes were not on the radar screen in 1990. And then they started looking at the deposits, and Brian Atwater's work, Kurt's work here, Portland State. They said, whoops, we may have a problem. And now we do. And now we know that this is earthquake country, but it was not on there. We were going to be shifting in Portland from Seismic Building Code 1 to 2B. We didn't have any earthquake hazard building codes. And so the buildings that were built before that had just minimal type of things for that. And so we had hats that said to be or not to be. That is the question. And then we eventually went to that, then to Seismic Building Code 3. The coast from Washington all the way to California is Seismic Building Code 4, except from Newport to Astoria. It should, in my estimation, be 4 also. And then basically from the Coast Range to the Cascade, Seismic Building Code 3. So we've upgraded it. We're there. But we weren't there before. And now the police departments are ready for big earthquakes. Fire departments, hospitals, schools, they all know what to do. But before 1995, none of that. If we had had a subduction zone earthquake back in 1990, this place would have been a disaster because we weren't prepared. So we've got those three big, huge earthquakes that occurred. We had Haiti, and Haiti was awful. Channel 8 came over for a sound bite 1 hour after it occurred. We'd seen it on the seismograph at Portland State, and I said it was a 7. They said, what is going to happen? We don't have any pictures coming out of there. We heard that one school collapsed. And I said, that is just the tip of the iceberg. First of all, it is a 7.0, which is huge. Secondly, it's very, very shallow, number 2. Third, you've got a huge population there. And fourth, that is a country with no building codes. It barely has a government, and I'm predicting that we're going to have huge numbers of buildings collapsing and everything happening, and sure enough, as it unfolded, it was exactly that. It's a movement of where the Caribbean plate is moving in a easterly direction, and the North American plate is moving in a westerly direction. It's a strike-slip fault, and the movement is like that. And all of you know the story. It is absolutely awful what had happened down there, and the rest of the world is going to be investing in that country for many, many years to help them put everything back. Then we had Chile. And oh my God, the Chile earthquake is an exact replica of the big one, the subduction zone earthquake that we talk here. And so now when people say, well, what's the subduction zone earthquake going to be like? I say, just look at what happened in Chile. 8.8, huge. 7th largest earthquake recorded in the world since the seismograph was invented. And shaking 2 to 3 minutes. 30 minutes after it occurred, they had a tsunami. 300 people killed in the tsunami areas, and 800 people so far have been recorded as dead. The effect on the infrastructure has been absolutely incredible. Last night was the inauguration of the president, and during the inauguration, they had another aftershock. But the good news is that that is a country that knew about it. The biggest earthquake ever to have been recorded since the seismograph was invented was in 1960. It was a 9.5. And so that country said, we live on a major plate boundary, subduction zone, the Nazca Plate, the fastest moving plate in the world, 17 centimeters per year, going down underneath South America. And so they said, so they have very, very strict building codes that you have got. But still, if you saw, there was one photo that was there of a new apartment building that split in half, and it was a new construction. Well, what happened, you had probably liquefaction of the soils underneath it, pulling the whole thing apart. And so that is what is going to possibly happen up and down the Pacific Northwest coast if we have a similar type of one. Our plate's only moving 4 centimeters a year, so therefore the rate, the period of time between different events is not quite as short as that one. That was only 50 years ago. And then Turkey occurred Monday this week at 5.9, and the next day they had an aftershock 6.0. Normally the aftershocks are a lot less. And now that's a country also, strike-slip fault, and huge number of earthquakes that are occurring in that particular area. I mean, Istanbul, every 300 years, a major earthquake. They just kind of rebuild the city, and then 300 years later, it gets leveled, and then they just rebuild it and goes back up and down, up and down. It's a fact of life over there. They had originally 51 people killed in Turkey. They now brought it back down to 41 because some of the people were recorded twice. But it doesn't matter. They were primarily mud houses out in the eastern part of Turkey where they didn't have any building codes. So we live in a geologically active environment. Lots of geological hazards. For me, it is absolutely wonderful for teaching my grad students who come from all over the world. We have lots of things to work with. And the theses, it's great. And I love interacting with the community, and I do an awful lot of work doing that. But we need to be prepared. And so that's why I am here. Portland State, we have a motto, let knowledge serve the city. And we try and reach out to the community and help in the decision-making process. And that's what I'm trying to do today. So thank you very much for coming today and listening to a little bit about the earthquakes in Oregon. And again, I have one last thing to remind you. Geology rocks. Thanks. So we have time for some questions. Oh, Jim gets to ask.
The first question for our speaker, as always, will be from our City Club host. Our host today is Jim Zarin. Jim is a partner at Stoll Reeves LLP, where he works as a real estate development attorney. He's been a City Club member since 1986 and has served as both chair of the research board and as City Club president. He's currently City Club's immediate past president. Jim?
Thank you, Scott. I think it's too bad he doesn't know his stuff and doesn't have any passion and can't talk. Scott, I think it'd be interesting for the audience to have you maybe comment on bridges in Portland. One of the most contentious and difficult public issues the region is facing is the Columbia River crossing, the I-5 bridge across the Columbia. And one of the things that is talked about all the time in the context of that discussion is the susceptibility of that bridge to earthquakes and seismic action. And maybe you could talk about how the risk level for that bridge compares to other bridges in Portland, and how people in your line of work talk about bridges and evaluating them, and how risky they are and how you deal with it.
Great. Thank you, Jim. Well, I know from my days when I was here in the club, transportation issues were always an issue. And I remember there was a guy in the club named Ray who always, every week, no matter what the topic was going to have a question on transportation. So, Jim, thank you very much for bringing that up. Bridges are a huge deal. And once earthquakes got back onto the radar screen here in Oregon, number one thing that we did is the state capitol. I mean, the capitol was closed down for a year as the Pioneer got realigned up on the top. Legislators said, we've got a problem, and so they allotted money for making of earthquake hazard maps and then tsunami hazard maps. And then ODOT, Oregon Department of Transportation, said, we better check out what is happening on all of our bridges. Another thing was we need to develop what is happening with Rockfall, because we have 1,500 steep slopes next to major roads in Oregon. And when you have an earthquake, a lot of rocks fall off. If you have a car driving by below, then you have a chance of getting hit. And so I'll deal with both of those. First of all, I'll deal with the landslides because our geologists and geotechnical engineers developed what is called the Oregon Rockfall Rating System. Which has now been adopted all over the world, and it is great for governments that don't have much money. And so it prioritizes where do you get your biggest bang for your buck and where do you spend your money first. And so they ranked all of the 1,500 rockfall potential areas based on the traffic going by, the geology, the height of the slope, the size of the ditch, 15 different characteristics. And so the money that was allotted every year went to the most dangerous, the next, and so they have been working on that for the last 20 years or 15 years. Did the same thing for the bridges. And the three top bridges that we have in the state that were first retrofitted was the I-5 bridge going to Vancouver, the I-205 bridge, first four, the Fremont, and the Markham. Jeez, I couldn't remember it earlier, too. And the Markham was very disturbing because the construction at the other end had the similar construction to the Highway 880 Nimitz Freeway bridge going from Oakland to San Francisco that occurred in 1989, the Loma Prieta earthquake, or the World Series earthquake down there. And they, whoops, we better. And so they went, if you remember, the lanes were tied off. You couldn't go into them as they put a lot of wires up there. And so they've retrofit those bridges. Boone Bridge down in Wilsville, the next major one that was done. And in fact, a lot of the I-5 bridges have been done since that time. And so the state, and actually we've got some very, very good earthquake engineering specialists here in Oregon, not only with ODOT, but at Oregon State University. That's where we've got the top guys. And so they worked with ODOT, and so they have retrofitted those bridges. Now, see, back before 1995, anytime you did any design work, you didn't worry about earthquakes. That was one thing that was not on the radar screen, and so the design work just didn't take it in. Now it is automatic. And so we ask, what is the maximum size, so the magnitude, and we deal with two of them. We have the 6.5 for the localized ones, and then the 9.0s for the subduction zones. Another thing we're worried about is the acceleration. How fast are these waves coming through? And one thing that was very disturbing that I just heard yesterday about Chile, it was in Santiago, the values got up to be about 0.2 G. And in Portland, all of our work here is designed for 0.2 G. But down on the coast in Concepcion, they got up to almost 1 G. That's 9.8 meters per second squared, for those of you who know your physics. And so higher than we had expected. And so the good news in Oregon is that a lot of our agencies are working on that. And they're on board, designing, prioritizing, and doing. The problem is we don't have a lot of money. So where are we down the list? We have a long way to go. So good question, Jim, to start this off.
So we'll now take questions from the floor. Asking questions at Friday Forums is a privilege of City Club membership. When you ask your question, please identify yourself as a City Club member and ask your question in 30 seconds or less.
Isabel Sheridan, a member. In Portland, there are 536 petroleum tanks with a 300 million plus gallon capacity. And they're situated on fault line, in an earthquake zone, fire zone, etc. What government agency, for example, DEQ, is exercising its jurisdiction to ensure that these facilities have addressed earthquake preparedness?
Absolutely, great question. And what we're talking about there is primarily northeast Portland, the area from St. John's down into the northeast industrial area, northwest Portland. Almost all of our gasoline tanks, all the gasoline coming in and going out of Portland, go right through there. It was with leading a field trip of geologists and engineers last Friday. We were out there. It's the area where old Giles Lake is. That area in there, the soils are absolutely awful. When we drill down through them, we ram drills down through them and we count blow counts. And so if it is really good hard soil, it may take 20, 25 blow counts to go 1 foot. Well, there were some places out there with 0 blow counts. The things it's soup like that underneath the ground. And on top of it, you got all these storage facilities, et cetera, of a lot of chemicals, et cetera. Our State Geological Survey is working with that right now. In fact, Mei Wong talked to me just on Monday about that. And so we are dealing with that. DEQ, Dogami, and then we're also putting another CSO, the big dig tunnels out there, that will be, they're taking that into consideration too as they're putting that in. But we have a lot of work to do out there. And earthquakes related to transportation routes, just taking a little step further, we have big problems up and down the gorge. What if we have major rock falls coming down onto our major railroads on both sides of the river, or a big landslide coming down? The Bridge of the Gods landslide, I still am a firm believer that that came down from the last subduction zone earthquake. But the dates don't bear me out, so it's probably something on Mount St. Helens. But good question. We're working on it, but we still have a long way to go. Next question.
Hi, I'm Greg Kafuri. It would seem that one catastrophic risk would be that a lot of the ancient buildings in downtown Portland would collapse. Our building is on 4th and Stark, where we have our office, which I understand is Phil, and subject to liquefaction. There may be hundreds of 100-year-old buildings in that area. Should they be condemned? Is it realistic that they should be retrofitted? What can be done? And who's looking at it?
And it has been looked at, so a very, very good question. All of the buildings that were built before 1995 we're concerned about. But then especially the old ones that are 100 years old. And first of all, unreinforced masonry, brick buildings, are the ones that don't respond very well at all in earthquakes. And so we're always concerned with those. And you don't have to, any place in the United States, you don't have to bring your building up to code. You only do that if you're going to do any type of building project. If you apply for a building permit, then you got to bring the whole thing up to code. And so in Old Town, a lot of the buildings have been brought up to code. Anytime you see these big X's, external structures, internal structures, that means that that building has been brought up to earthquake standards. But a lot of them haven't been, because they haven't had to do any changing. They haven't had to have a building permit. The state has looked at those, and they are saying, look, we don't, unless they do major changes in the building, then we are not going to require them to do that. The question, some people have been saying, yes, we need to do that, but that's a huge monetary outlay. But then we have the potential of loss of life, et cetera. And so those are things to ask. You know, if you're looking for an office space, always ask them, is this building been brought up to code? And it's very important. Portland State, we are retrofitting all of our buildings slowly but surely. It takes a lot of money and time. Yes, good question.
Linda Geron Mills, City Club member. The reason, or what I would like to know is what the state of episodic tremor and slip science is, and where that's being used in prediction.
Well, good question. And so how do we get those recurrence intervals and the episodes of when they have occurred in the past? In California, about half the geologists, and there are a lot of them down there, what they do is looks like a building is going to be built on a fault. You go out and you trench it. And then what we do is we get down in there and we look for the buried soils that have been created every time that there has been a movement. Then you date those, then you put together your recurrence interval. And so that's the traditional way. But we got some neat new toys to play with, and these are called GPS units, Global Positioning System units, that are very, very accurate, down to less than a millimeter in length. And so what we can do is we think we have a fault, and Chris Goldfinger is one of the guys in Oregon who's doing that. If we have a fault, and we don't know if it's active or not, what we can do is put some concrete into the ground, attach a global positioning system to both sides of the fault. So, and then what we do is we go back out and read it every year. And if it is moving, it is going to be, you're going to be able to see that. And the nice thing is you can tie these in with a satellite, and you can, in your office, download those things. And what we are seeing is the strain building up. So we're saying, is this fault active? Well, there's movement. Yes, it is active. And how is the strain? Now, the question is, we've only been doing this for a few years, and so eventually we're going to have a big earthquake. And then we're going to have all that strain data from all of those GPS units, and we say, oh, once you get to this amount of strain on this particular rock, bingo, that's when the earthquake's going to happen, and then we can put out the earthquake predictions. That's coming down the road, but it is something that really excites me, that the potential for that is coming. Thanks. Next one.
Hi, for all of us, I'm Ann O'Neill, a member of City Club. For all of us sitting out here with dark clouds over our head, we love your enthusiasm for your subject. But let me ask, as a general reader of the newspaper, it seems to me over the decades that earthquakes occur about 4 in the morning. Has there been any study? Do they always show up before dawn?
You know, they do occur at all different times that they do. But, you know, the spring break was one of those early morning ones that we have got. But then the World Series quake was right at 5 o'clock or 4 o'clock in the afternoon. There are some relationships to the moon. And some people have taken a look at that. When the sun and the moon are all lined up with the Earth, there's a greater amount of pull on the Earth. And it seems to be that there's a greater number of earthquakes at that particular time. I don't know of any studies about time of the day, because 4 in the morning here may be different time, you know, in different time zones. So I don't have a good answer to that. But good question. Yes?
Barnes Ellis, and my question is this. The next time we have a smaller earthquake, should we feel good in the sense that pressure is being relieved gradually, or should we feel anxious, it's probably a precursor of something bigger, or is it something you just don't know?
And that's a wonderful question. You know, when you have an earthquake, is it a precursor to something bigger, or is it relieving pressure? Obviously, it is relieving pressure. That's very good, but it's relieving pressure on that particular fault that you have got. And so it may be a little tiny fault, and it's not the big one that you're concerned about, like the Loma Prieta earthquake that occurred in 1989 in the Bay Area. That was not on the San Andreas. And still in the Bay Area, they're still concerned about movement on the San Andreas Fault. And then you have got the fault on the other side of the bay called the Hayward Fault that goes right through the football stadium at Cal. Now, I went to Stanford. We have a little game every year called the Big Game. And so we don't mind if something happens over on the Cal campus. But no, but that's probably the most dangerous one that is there. And so the U.S. Geological Survey are some of the leaders in the world in figuring this out. And that is always a question when an earthquake occurs: is this a precursor to a bigger one, or is it just relieving pressure on that particular fault? And so the Loma Prieta, the question there was, is that a precursor to the big one occurring on the San Andreas? And so right now we don't know. But there have been some instances where they were. And we've got some examples of those. They're smaller ones. And probably give us another 10 years and maybe we'll have a better answer on that. But that is a valid question that we're still working with. Yep. Yes?
Carol Wallace, I'm a City Club member. Growing up in Oakland, California, where there are a lot of small earthquakes, we were told to stand in doorways. And now after the Haitian earthquake, some of that's been questioned. I now live on the 10th floor of a condo built in 1973. Does it make any difference where I stand?
Yeah. the one thing, first of all, where do you stand? I mean, if I'm in an earthquake, I still go to the doorway. And because that's the strongest place structurally. There was for a period of time, for a couple of years, there was a paper that was put out by a guy who said he worked for the Red Cross, and he called it the magic triangle. And he said, don't get in doorways, but actually hide right next to a desk, because if the roof collapses, then there'll be a special place for you to be. Now we have found that none of that can be substantiated. And so there have been major papers that have come back. So I still go and stand in the doorways. The good news is, we didn't have required earthquake standards before the 1990 when we went up to Seismic Building Code 2B, but a lot of the building that was going on actually encompassed a lot of the important things just because of the way that they were building, especially taller buildings, and the way that they were also building the foundations. But I'm not an engineer, so that's really a question that an engineer is going to have to take to the next degree. But the newer buildings, the tallest buildings, are probably going to be the ones that are going to do the best. All the ones that are down in John's Landing. That's liquefiable soil down there. And I still remember back in the 1990s when they were planning that, and a friend of mine who went to Stanford with me called me up, and he was down in Salem and government. He said, well, what do you think about building tall structures in John's Landing? I said, well, that's liquefiable soils. That's a problem. Just make sure that they do that. And some of those have pilings that go down almost as deep as the building goes up. And so they're going to do fine. The soil may liquefy underneath it, and they be out there as an island, but they're still going to be standing, and so they're going to be built right. But, I think hopefully you'll be fine in that, but there are no guarantees. Yes, next one.
B.J. Seymour, City Club member. For many of us, the worst disaster we can recall in this immediate area was the Columbus Day storm of '62. Can you possibly compare that with the likelihood of something worse from an earthquake?
Yeah, and I do remember the Columbus Day storm, because that was my high school, that was our fall. Well, it was our big football game that we were having. We had a parade in downtown Beaverton. All the floats blew apart. And then everything blew down, and they canceled the game, and it was incredible. But, we did not have a lot of loss of life from that, but we had a huge amount of damage that we had, and a lot of people were messed up with trying to get around, and no power for a long period of time, and so it was difficult. A subduction zone earthquake there's going to be an awful lot of damage. Along the coast, if it occurs in the wintertime between here and the coast, there are going to be numerous amount of landslides, and trying to get help from here down there is going to be very difficult, and the coast is going to have to fare for themselves for a certain period of time until help can get in. But we're going to have loss of life. And this is the bummer thing that goes along with this, and that's why we're trying to let people know about this, so at home, everybody can have their home earthquake kits. They can take their water heaters and tie them down, know where the wrenches are to turn off the gas and things like that. And schools, they have kits for all of the kids, everything like that. But it's going to be a lot worse, and that's especially along the coast, but even here with our wave amplification in the Portland area and the older buildings having bigger problems. Okay. We just need to be prepared. Next question.
Well, I think you may have answered my question. I'm Lee Stevenson Kuhn, a member, but what should we do to prepare for the big one?
Oh, yeah, okay. Well, personally, everybody's house has got to be ready. You have your earthquake hazard kits, flashlight, some type of radio that doesn't need electricity, a water supply. Make sure that, because if you lose electricity, your water heater is going to be a major source of water that you can drink from. And then if you have gas in your house, turn that off immediately. And in fact, if you go onto the Red Cross, or just Google earthquake hazard kits, personal home earthquake hazard kits, they have a listing of all the things that you should do. And then secondly, in each one of our neighborhoods, I gave a talk 2 nights ago to a whole bunch of neighborhoods, every neighborhood should be getting together. Get to know your friends. If you've got kids in that neighborhood, they are going to be, what do we do? Where do we go? If mom and dad aren't here, or even if they are there and they're just off at the store or someplace like that, you need to have a plan, and everybody needs to know where you can turn off the gas in all of the houses, and go to Sally's house if you're a kid, because of that. So helping out plans need to be done. As I said, locally, our jurisdictions are doing a good job. We have practices that occur periodically for earthquakes, and if we have an earthquake of this particular magnitude at this particular area, what's going to happen? Hospitals are much better prepared. Everybody's much better prepared. Thanks. Good question. Next one.
Steve Shell, member. On the Oregon beach, you've indicated that you're going to have a tsunami, but preceding that is a drop in the soil. You'll have 20 feet here, I don't know, 1 to 2 meters is what you said, down. Is that the same all the way down the coast, or will it vary depending on whether you're on the northern coast or the southern coast?
It will vary all the way up and down the coast. And so, yes, you will have variable sinking. But on the average, that 2 meters, 1 to 2 meters was what we have found. And again, Kurt Peterson in my department found all that. Interesting thing is happening along the coast. In the 1920s, we imported a plant called European beach grass. European beach grass was put into the dunes up and down the coast. It's an invasive species that has really helped Oregon, because what it does is when the sand blows off of the beach, hits the plant, it goes down to the bottom, plant continues to grow up. And the dunes that are right in back of our beaches are called the foredunes. Before the 1920s, we had foredunes that were maybe 2 to 3 feet high, not very high. The spits only had 5 feet of relief, and so every time there was a tsunami, go right over the spit, all that sand would go into the bays. Now on the spits, we're getting dunes that are up to 50, 60, 70 feet high. And the foredunes up and down the coast are also getting very, very high. And what are they doing? They are creating natural tsunami barriers for the people living on the coast. Now, a lot of the people in older houses want to see the ocean and see the waves coming in. And the tendency is, let's knock those suckers down, I want to see the waves. Well, what you're doing, Mother Nature has given you a natural barrier. And especially if it's going to be a tsunami that's maybe 5, 6 feet high. It may be coming into the house, but with the sand dunes there, it would be helping you. Yes?
Paddy Tillett, have you found any correlation between major subduction events and volcanic activity in the Cascade Range?
That's a great question, and people have actually looked at that. And so far, no correlation that is there, because remember, that plate is being subducted down, then it's melting, and then coming back to the surface. A very, very slow process of the conversion of that melting of the plate and then going into the individual volcanoes. And so, so far, nobody, and we have, I mean, Chile is a major subduction zone, the Aleutian Islands, Japan, Philippines, all of those, Indonesia, all similar subduction zone areas that we have got. And nobody's come up with one, but it's, and they have started looking at it, but maybe someday we will see that.
We've run out of time for further questions, and we'll have to stop for this week. Please join us on March 19th to learn about the future of renewable energy here in Portland. And as we close, please join me in expressing our appreciation to today's speaker, Scott Burns. We are adjourned.
Thank you, Karen.